Hey everybody. All right, so today we're going to do another workshop in SimVascular. And so, I do want to talk about some things before that. And so if you want to start up SimVascular and download the demo project that I uploaded onto Canvas, then we can basically be set to go for today. Okay. All right, so actually let me bring up the slides first. Okay. And we're going to be talking about a lot of CFD stuff today. Okay.
Professor,
Yep, what's up?
in 410, you had said that you had students in the past that did something FEA related to earthquakes.
Yes. Yeah. So they did, and so that was an interesting project because they kind of had to simplify it a lot from what they originally wanted to do. And so actually their report was actually a good one that I'm going to post too. And so you can actually look at that one and kind of see what they did. But basically what they had to do is they had to simplify their building geometry pretty significantly, just because it was the building geometry was a little bit too complex for ANSYS to handle. But then they were able to, I think, to apply like a shaking kind of load to it to simulate earthquakes. And so it's been a while since I've looked at it, but I'll post the example so you can kind of see what they did.
Do you remember how simplified their geometry was? Was it reduced to like beams and stuff?
Basically, yes. Yeah.
Okay.
Yeah.
All right. It's just gonna be kind of weird if I want to do something like that and you post it. Oh, whatever.
I mean, it's as long as you don't do the exact same building, because every building is different, and so as long as you don't do the exact same building, then it's okay with me. Yeah.
Okay. Thanks.
Yeah. All right, it's 5:30, so let's go ahead and get started. All right, good evening, everyone. How's everyone doing today?
Good, Professor. How are you?
Good, good. Last week before spring break, and so it's always the toughest week to get through, just because I think everyone's kind of anticipating spring break after that. But hopefully, this week will be fun for us because this week I just want to focus on just doing the CFD. Um, Partially, because the last workshop kind of took a bit longer than I expected, and so I want to kind of definitely leave a good amount of time here, and also partially because I don't have the other stuff prepped at this point, and I didn't, and I don't think I'll have it prepped by Wednesday, by Thursday as well, and so I'm gonna definitely need the spring break to prep on what's coming next, and so you guys get to peel back the curtain a little bit and see that it's you know. A little bit not as prepared as I want to be for this week, but it's fine. And so, we'll really get to spend a lot of time with the CFT and really talk about, a lot of the stuff. And I want to come at this week with kind of the perspective of, even though we're going to be using SimVascular, which is obviously, very niche software in kind of the world of computational fluid dynamics. But what I hope is that, a lot of the concepts and a lot of the, the knowledge that you get from this, you can apply that to other CFD solvers as well. And so I'm going to kind of approach this week from that perspective. Okay. And so with that said, hopefully everyone got my email earlier today, and that just to kind of make sure that we're all on the same page, I've, oops, this is not for this class. I've uploaded kind of a SimVascular project for us all to kind of work with together, just so that we all, can kind of, use that same one. Okay. And so if you go to our website and you go to files and you go to project, you can see that there's a zip folder here called demo project.zip. And so this is essentially kind of the same demo project that's on the SimVascular website. I just trimmed some of the files from it just so it's not so big. And so instead of being like 150 megabytes, I trimmed it down to 30.5, which will be just fine for what we're going to do. Okay. Okay, and so the other announcement I want to make is that I finished grading your midterms actually just this morning. And so I believe the average was about 42 out of 50. And so that's about an 84%. So you guys did really well. And so, you guys should be able to see your grades on Canvas right now, along with some of my feedback. And so generally the way I do feedback is that if you got full points on the problem, then I don't really leave you any comments then. Just to kind of make life easier for me, just so I don't have to keep writing, great job, And so if I don't leave you a comment on a problem, then it implies I'm saying good job, and I'm kind of high-fiving you at the same time. But if I do take points off, I always like to justify, why I'm taking some points off. And so definitely read the comments that I give you, and if you feel like, that I graded you too harshly or I made a mistake, definitely let me know. Especially with this class. We had mostly conceptual questions for the exam, and so definitely let me know, and I'm always open to discuss those things with you. And a lot of times I do end up making mistakes or grade things too harshly because I didn't read them carefully enough. And so definitely read the feedback and let me know if you think I made a mistake, and I'm always happy to go back and correct and give more points if I if you guys deserve it. Okay. And so the solutions are not posted yet, but I will post the solution. I will post my solutions probably sometime tomorrow morning. And so you can find the solutions here, and I'll link it from the course website as well. Okay. Okay. And so any questions on anything before we get started today? Okay. Oh, I lost the chat. Let's see. Okay. All right, and so let's go ahead and continue where we left off. And so last Thursday, we were going through these lecture slides, which I called, Introduction to Computational Fluid Dynamics. And so we've gone over kind of most of the slides here. And so we talked about generally, what is CFD, what is it used for? You can simulate flow of air around an elephant if you really want. And what are the general steps to run a CFD simulation? And so, just because we're going to be running through these steps, for the SimVascular workshop today, I do want to run through these very quickly again. And then I think there were, the last 3 slides that we didn't get a chance to go over. And so I want to finish those up. Okay. And so let's start today by just kind of summarizing, and going over quickly, what are the general steps to run any CFD simulation. So not just SimVascular, but for any software that you want to use. Okay. All right, and so step one for running a CFD simulation is always define the problem. And so if you remember, before you start, any kind of analysis, whether it be CFD, ANSYS, pen and paper experiments, you have to define, what your engineering problem is, and what you ultimately want to get out of your analysis. Okay. And so, things usually aren't done just for the heck of it, in out there in kind of the real world. And so usually, if you're going to take the time to set up a simulation, or you're going to take the time to set up an experiment, and to, and to perform an analysis, it shouldn't be just for nothing. And so it shouldn't be just for, just for producing something that looks cool. So oftentimes, you have some kind of, engineering question that you want to answer. You have to define, what your problem domain is, what are the relevant physics, and what are the expected results, right? And so before you even start, you have to think about, what's the engineering problem, or what do I want to get out of the simulation before you even begin? Because that's going to drive, a lot of the decisions that you make kind of down the road from here. Okay. All right, and so the next part is to model the geometry. And so since you're going to be running your simulation on a computer, you have to have a computer representation of the geometry where you want to run your simulation. So most often, this takes the form of some kind of CAD file. And so, people use SolidWorks a lot for this. Okay. But in our case, our model is going to be produced by SimVascular. And so that was the subject of our first workshop. Okay. Because if you remember at the end of the first workshop, we produced basically a solid model of our blood vessels, which looks, something like this. Okay. And so this is kind of the solid model that we're going to be looking at. Okay. All right. And so the key point that I want you guys to remember here is that when you're running CFD, remember you're simulating fluid flow. And so basically you need to model your geometry such that you create your geometry for the places where the fluid's going to flow. Okay. And so if you want to simulate flow in a pipe, you don't want to make some kind of hollow geometry, what I have above here. What you want is a solid geometry of the empty space, within the pipe. Okay. And so you want something like this. Okay. All right, and so the next step, which we'll spend a good amount of time talking about today, is the meshing, right? And so, meshing basically takes your geometry and breaks it up into a bunch of really simple shapes, okay? And this is really important because, a computer can't, take something complicated like a fighter jet right here and solve Navier-Stokes on it. And so what it has to do is it has to basically break this up into a bunch of simpler shapes and then solve Navier-Stokes on this simple shape, because that's something that you can easily program. Because it's very hard to write a program to solve Navier-Stokes on a complicated airplane like this. But if you break everything up into like triangles or tetrahedrons, you can easily write a program to do that. And so by breaking up the geometry into the simple shapes, you basically make it so that your computer can solve your equations for you. And what's going to be important for the meshing is how many elements and nodes that you end up generating in your mesh, right? And so the more elements and nodes that you get, generally you can expect the simulation to take longer. And so basically you can think of it as, for every node every element and every node that you produce, you're having the computer solve for the solution at that node. And so more nodes means more work for the computer to do. Okay? But it also means more accuracy. And so the more fine your mesh is and the more elements that you have, the more accurate your simulation is going to be. And you want your simulation to be accurate because, a simulation that gives you wrong results is not useful at all. In fact, it's kind of just a waste of everyone's time. And so you want to always balance these things. And so you want to give your simulation enough elements that you get, good accuracy, but you don't want to do too many elements such that your simulation takes weeks to run. And so there's kind of a balance, and we'll talk about that, later on when we get to SimVascular stuff. Okay. All right, and so the next thing is boundary conditions, and so we'll spend a good amount of time today talking about that as well. And so a big part of running simulations is that you have to define what the simulation results are going to be at the extremities of your domain. Okay. And so for our case with SimVascular, this means defining what the solution is going to look like on the lateral walls. And so, on these, lateral surfaces here and on the caps. Okay. And so defining how the solution behaves at these different surfaces is going to be a big key to running the simulation. Okay. And so, I'll go over this kind of quickly now, and then, we'll talk about this a lot more later. But There's different types of boundary conditions depending on whether, you want the flow to pass through that surface or whether you don't want the flow to pass through. Okay. All right. And so the next step, and so this is kind of one of the last things that we did last time, is we need to specify other solver parameters. Okay. And so things like, what are the density and viscosity of the fluid? Things like, the time step size, or how much time do we want in between the frames of our simulation, and the number of time steps that we want to solve for. Okay. And things like, how often do we want to save the results, and a lot of kind of miscellaneous parameters that that can affect the results if you're kind of struggling with some other stuff. Okay. All right. And so once all that is done, you have your mesh, you have your boundary conditions, all the parameters are set. Now it's time to run the simulation. And so for today's workshop, we're going to do a simulation, a very simple simulation that you can run it on your computer. Granted that you have, a decent enough computer, and so, I'll run a simulation that I can run on mine. But depending on how your computer is, it might not work that well. Or if you have a better computer than mine, you might be able to do more. But more likely than not, for most simulations that are practical, you're going to need some more firepower than what's in your personal machine. And so we're going to be running our simulations on a supercomputing cluster. And so probably we'll do that on Thursday, because I don't think we'll have time to get to it today. Also, you guys need to make an account and things like that. And so, I'll send instructions for that tomorrow, so that, we can get this rolling on Thursday. But typically, when you run the simulation, you run it on a supercomputer, just because you just have a lot more firepower and a lot more processor there to run your simulation. Okay. And then even on a supercomputer, your simulation can run anywhere from, it can take anywhere from a couple minutes to several weeks. And so, it's, you say, I say several weeks, and that it's, it literally takes, you hit go on the simulation, and then you have to wait 2 weeks in order for you to even see, if your simulation worked out or not. And so, there's a lot of computational fields that actually do that. And as you can imagine, it's terrible that if you're running your simulation for weeks and the cluster has a blackout and you lose all of your data. And so that's always a terrible thing. But for this class, I would say at the very most, it would probably only take you maybe a couple hours to run a simulation, because we're not going to be running too difficult. Nothing too difficult. Okay. All right. And then once the simulation is done, you're not done at that point, and so you need to basically download the results and analyze them. Okay. And so at this point, you can load your software into a kind of a visualization software. And so we're going to be using a free one called ParaView. And so, I'll put a link to that, on the Canvas site for Thursday as well. But basically, you need to put your results in a form that you can actually view them. Because a lot of times when you just take the simulation results by themselves, they're in a file format that you can't actually work with. And so usually what you need to do is you need to convert your simulation results into a form that you can actually look at, and then load those results into an appropriate software where you can view the results. And I'll show you what it looks like today. But I didn't ask you guys to download ParaView for today. And so, I'll let you guys kind of explore that more on Thursday. Okay. Okay. And so that was kind of just a quick summary of, the steps to run a CFD. And so we'll go through all of that today in SimVascular. But before we go to SimVascular, I do want to talk about a little bit about high performance computing, because you guys are going to be running, your simulations on a supercomputer, and with that comes some etiquette and some basic knowledge that you should know, so you don't, and so you run things properly. Okay. All right, so let's define this first. And so high performance computing, and so oftentimes it's abbreviated HPC. Okay, and so it basically refers to the use of any kind of supercomputer for performing analysis or simulations. Okay, and for supercomputers, the way I'm defining that here is any kind of computer system with hundreds or thousands of processors. Okay, and so if you look into a server room with for a supercomputer, it looks something like this. And so you have basically like a bunch of rack-mounted servers, and so these are, each of these, it's a bit hard to see, but, each of these different lines in this rack right here represents, a computer that might have anywhere between like 8 and 24 processors on them. And so they're pretty impressive. And so they're basically optimized for performing a lot of calculations. So these computers here, they're legit computers. And so, they might not look like your laptops or a desktop machine. And that's because they've kind of stripped away a lot of the things that they don't need for calculation. So things like a graphics card, things like, HDMI ports, things like, the sound cards, Wi-Fi cards. And so, it strips away a lot of those things. So it really maximizes the space for just the CPU unit, in order to perform calculations. And so from this, for like a single, rack mounted machine like this, they're able to jam in here, maybe like a few hundred processors. Whereas for, like a regular desktop machine, you might have anywhere between, 4 and 8 usually, depending on, how powerful your machine is. Okay. And the thing to know about these supercomputers is that, they're remote systems. And so what that means is that, we're not physically going to take a field trip to a supercomputer. And so, you're going to access these remotely through the internet. And so actually, the supercomputer that we're going to be working with is physically actually not too far. And so the one we're going to be working with that is actually in San Diego. And so which is kind of unique, because a lot of times you're working with a supercomputer that might be on the other side of the country, might be in tech. A lot of them are in Texas, actually. And there's, I think, a big system in Tennessee too. But our cluster is actually going to be in San Diego, which is not too far. But we're not going to drive there. We're just going to upload our systems, upload our files onto there. Okay. And so, this is important to know because, your simulation files, they basically have to be manually uploaded and downloaded by you, the user. Okay. And so I want you guys to kind of keep that distinction in mind. Okay. And so traditionally, if you want to access a supercomputer, typically this is done by command line. And so, if you've never seen the command line before, I can kind of show you, what that looks like. It's basically a text terminal like this. And so if you've used Linux before, you're kind of familiar with this. You can use that with that. But the cluster that we're going to be using is, is not going to be accessed through a command line like this, because learning command line is kind of, takes a few weeks of practice itself. And so, the supercomputer we're going to be using uses a web interface, which is, kind of makes it easy to kind of upload files and run simulation from there. But traditional access to a supercomputer is done via command line like this. Yeah, didn't Texas lose power not too long ago? Yeah, actually, I'm wondering about that too. So it's for me, actually, it's been a while. So I ran a lot of my jobs in Texas, at the University of Texas, actually at Austin, UT Austin, and so they have a huge supercomputer there. And so I used to run my jobs there, but I haven't done that in a few years, and so I don't know how the power outages and all the snow affected them. I imagined it was not good. But the extent of the damage, I'm not exactly sure, but I'm hoping that they're okay. Yeah. Right. And so another thing that you typically have to do on a cluster like this is that you have to install your own software. And so the term we give for that is compile. And so typically you have to compile, if you want to run SimVascular on a cluster, you have to kind of compile it yourself. Just kind of speaking from experience, and other people who have tried this will tell you that compiling software on a cluster is a huge pain in the ass. Like it's never easy, because whenever you compile something, you have to your installation usually depends on a lot of software packages, and so you have to make sure all of those align properly. But then you also have to make sure that it doesn't break anything else on the system, and so it's a huge pain in the ass. But luckily for us, for the supercomputer that we're going to use, the SimVascular has already been pre-installed, and so I've basically already kind of done that for you, and so you don't have to worry about that. So we can kind of just use it as kind of just like a remote system. But if you do plan on pursuing this kind of work after this class, just kind of be prepared that you're gonna spend quite a bit of time wrestling with the cluster and trying to compile stuff. You're probably gonna have to contact IT support from the cluster and to kind of help you with that, because it's not easy to compile code. But luckily for us in this class, I've kind of streamlined most of that process for you, and so you can kind of just use it as kind of like a computer that's not here. Okay. And so, that's kind of more just trivia stuff. And so just kind of background on supercomputers in general. But the practical things that, that you're going to have to worry about in this class is that you're going to have to select cluster parameters. And so these are some additional parameters that you have to select on top of your simulation parameters. Okay. And so primarily what you have to select is how many processors do you want to devote to your simulation jobs, and how long do you plan on using the cluster. Okay. And so, these cluster systems, they have, literally thousands and thousands of processors. But for any simulation, you're not going to use all 1,000 processors at the same time. because you just don't need it. You don't need it. And also, the cluster is a shared resource. And so what that means is that, you're not going to be the only one using the cluster at a given time. And so this cluster is going to be used by, obviously, everyone else in the class is going to be using this cluster. But, I can tell you, that this cluster that we're going to be using is used by researchers, all over the country. And so, because it's a shared resource, you can kind of think of it like a community pool, right? And so, you have to kind of show, a bit of etiquette when you're using a shared resource like this. Like you can't go to the community pool and then piss in the pool and expect them to be happy, to welcome you back to the pool after that, right? And so you kind of have to use the shared resource responsibly, in order in order to use it well. And part of that is to basically not, and basically what that means is, you don't want to hog up the entire cluster for your job, especially if you don't need it. And so a lot of the etiquette that goes into using a cluster is to basically only use the resources that you need. Okay. Right. And so, when you're choosing the number of processors, generally what you can expect is that if you devote more processors to your job, it's going to finish faster, right? And so as an example, like if you use 24 processors for your job, and let's say that it runs in about maybe half an hour, if you use 48 processors, you can roughly expect that the simulation time will be cut in half because you're using twice as many processors, right? And so, if you use 48 processors, probably it's going to finish in 15 minutes. But you have to be aware that there are some diminishing returns, and so you can't devote so many processors to your problem and expect it to always have that kind of speed up, because eventually you're gonna run into the problem of having too many chefs in the kitchen, right? And so you can't take your same problem here and devote like 500 processors to this and expect it to finish in like 3 minutes. That's just not how it works. And so just as an example, think say like, you're working for a catering company and you have to prepare 100 sandwiches for catering, right? And so if you try to do this job with just one chef, that one chef has to produce 100 sandwiches, that's going to take him a lot of time. But if you assign 10 chefs instead, you're going to finish the task in 10% of the time, because each of the chefs can prepare 10 sandwiches, and then instead of one chef having to prepare 100 sandwiches, 10 chefs have to produce 10, and that's good, right? And so you have a 10x speed up in that case. But if you take the same task of 100 sandwiches, you can't throw 1,000 chefs at the problem and expect it to be done in an amount of time, right? Because if you throw 1,000 chefs, most of those chefs are just going to be sitting there doing nothing. And so you basically run into the problem of there's not enough work for the amount of chefs that you have, in the kitchen. And so, if you, throw 1,000 chefs, you're going to run into diminishing returns. Okay. And so parallel processing is the same way. And so if you want to jack up the number of processors, you have to make sure that each of the processors has enough work, in order for you to get an appropriate amount of speed up. Yeah. What if you hire Chef Gordon Ramsay? If you hire Chef Gordon Ramsay, then he will just yell at all your chefs. He'll say everything is raw and that everyone will be an idiot sandwich. But it's it doesn't solve the problem of 1,000 chefs creating 100 sandwiches. Yeah. And so for SimVascular, here's kind of my general rule of thumb. And so, you'll see that, when we produce our mesh, you'll get a statistic for how many elements that you have in your mesh. And so generally what I like to do is I take the number of elements and I divide that number by 20,000. Okay. And if you divide the number of elements by 20,000, this will give you the amount of processors that you should use for the simulation to give you an efficient simulation. Okay. And so let's say that you have a mesh with, 100,000 elements, right? And so you take 100,000 and you divide it by 20,000 and you get 5. And so that tells you that you should use probably 5 processors for the simulation, because 20,000 elements worth of work for one processor is usually a good amount of work for it to do. Yeah. I have to admit, I do enjoy watching Gordon Ramsay shows. Yeah. Yeah. Actually, my favorite shows that he does are actually the ones where he doesn't get angry. So actually the shows that he does like with his kids, I think he has a really cute dynamic with his kids. They seem really close, and he doesn't curse and get angry and stuff like that. So I actually enjoy those a lot more than when he's, getting angry and shitting on people a lot. Yeah. Yeah, yeah, the UK shows definitely have a much different vibe for that. Yeah. Okay, so any questions on this? So I know a lot of this might kind of seem like, it's kind of a lot of information right now, but, I want to kind of introduce this now because over the next 2 class periods, we're going to kind of see all of this kind of in action. And so, if you didn't, catch everything and if it's not sinking in right now, that's okay. And so, once we kind of visit this stuff, in practice, a lot of this will become hopefully a lot more clear. Okay, and so now let's jump into SimVascular. And so let's see how we actually set up a CFD simulation in here. Okay? And so remember, I'm working with the demo project that I uploaded onto Canvas. And so if you want to download that and follow along, you can. And I did this just to kind of make sure that we're all kind of on the same page here. But if you just want to, just sit and watch right now and then kind of refer to the recording later, that's perfectly fine too. Because ultimately, this workshop is just to kind of help you guys out with your final projects and to make sure that you can set up your simulation for that. Okay. All right. And so basically we're picking up basically where we left off from the last workshop. And so from the last workshop, you have a geometry that looks like this. And so after you've done the paths, after you've done the segmentations, after you've done the model, then you have your geometric model here. And so this is kind of like, after you've produced the CAD model for your simulation. Okay. All right. So one thing I do want to point out before we go to meshing is I want to basically point out some qualities of the surface. Okay. And so in particular, I want to look at the regions where, you'll probably have a vessel that branches off from another vessel. Okay. And so you can see right here from the color coding that we have, this blue vessel is branching off from this purple one. Okay. And so this vessel actually does a really nice job of this because it's the demo one. So it's really nice and pretty, but you can kind of see from here that the transition from the purple to the blue, it looks the surface looks very smooth, right? And so there's really not any sharp corners like this. And so this is good. And so this is generally what you want from your geometry before you set to mesh. Because what can happen is that if you have a lot of sharp corners in your model, and that typically happens, when you have branching vessels that come off like this, that can make things difficult for the meshing. And so, typically what I like to do before I go to mesh is I like to smooth the surface. Okay. And so we didn't get to do this last time. And so let me go ahead and show you how I smooth the surface. And so after you produce your model, you have kind of a list of surfaces here on the right. And then what you can do is you can highlight all of the wall surfaces. And so you can see here, as I'm clicking these, I'm highlighting the different surfaces, right? And so what I want to do is I want to highlight all of the walls. And so I'm going to hold down Control with my other hand, okay, and make sure I select all the walls. And so you can see now all the walls are highlighted in yellow, okay? And then what I want to go from here is, on this right-hand side for this SV modeling tab, is I want to go down to local ops, okay? And local ops will basically allow you to modify the surface of this model, to help things easier with meshing. And so what I want to do here is I want to smooth out this this junction right here to make it smooth, okay? And so from that, under local ops, I'm going to go to this tab right here called CSTR smooth, and that stands for constrained smooth, okay? And so what constrained smooth is going to do is you can kind of think of it as like kind of a smoothing function that you have in MATLAB, where it's going to smooth, kind of apply a nice smoothing filter over this surface. And so any kind of kinks or any kind of sharp corners that you see here will be kind of smoothed out, okay? And so with all these highlighted and with constrained smooth here, what I'm going to do is I'm going to click smooth local right here, and that's going to smooth out these this junction, okay? And you can see here, it kind of did a little bit. And so you can see, let me go ahead and Control Z, and I want you to kind of focus on this line that exists kind of in between these 2 points right here. Okay, so let me go ahead and undo, right? And so you can see when I undo here, you can see there's a very clear line in between this branching vessel and the parent one, right? And so when I click Constrain Smooth, what it did was it kind of performed this like little fillet in between that line right there, so kind of smooth those that junction out. Okay, and so I would highly recommend for your project to do this because it's this smoothing right here will make your meshing go a lot smoother. Okay, pun was not intended, but it kind of came out that way, right? And so, this smoothing, it's kind of good that, all of you guys have backgrounds in SolidWorks. And so you can almost think of it as like a fillet that you're applying here, because that's going to help us out, a lot with the meshing. Okay. All right, question. So can we do it at the end, or can we do it, or do you recommend doing it after creating each junction? And so you can do it at the end. And so you can basically wait until all your vessels are completed to smooth. And actually, I would recommend that better. So then you can kind of smooth all at once. And so I would definitely make all your vessels first and just do the smoothing right before you mesh. Yeah. Mm-hmm. Yep. And you can smooth more than once too. And so, actually, if you click smooth again, it's going to apply the smoothing. And you can see this, the surface was kind of affected again. And so you can apply it again, but don't do it too much, because then otherwise you might lose a little bit too much detail in your model. And so, use the smoothing, but don't go too crazy with it. But a little smoothing can go a long way for these models. Okay. All right. Any questions on this? Okay. All right. And so that's smoothing. And so, I would, strictly speaking, it's not required. And so, if you do a good job with your model, you can probably produce a decent mesh with that, without any issues. But, the smoothing does make things go a little bit smoother if you have some kind of tough junctions there. Okay. All right. And so the next thing that we're going to do is we're going to produce a mesh onto this model, right? And so if you recall, the meshing step, what we're going to be doing is we're going to take this, this relatively complicated geometry here, and then break it up into a bunch of simpler shapes that the computer can use for simulation. Okay. And so I'm going to right click mesh right here. And then I'm going to go down to here, this option right here for create mesh. And so you can see for this project here, there's already a mesh there. And so you can go ahead and, oh, I guess it's not loaded. But, so there's a mesh already there, but we're going to go ahead and create a new one. And so we're going to right click mesh and then click create mesh. Okay. And it's going to ask you to give a name for your mesh. And so again, make sure you give a descriptive name right here. And so I'm going to call, since demo mesh is already created, so I'll call this test mesh. Okay. And then, all the other options here, you can leave the same. And so you don't really only have one option. And so you can go ahead and click OK. Okay. And then after you create your new mesh right here, you can go ahead and double click that. And it's going to change this menu on the right here for all your meshing, for all the meshing options. Okay. Right. All right. So is everyone that's following along, were you guys able to create a mesh object and get this menu to appear here on the right? Great. Excellent. Okay, and so now let's create a mesh. And so, there you can see here, there's a lot of options you can do with the mesh. And, I'm not going to have time to go through all of these, but there's a lot that you can do. But the only thing you have to really specify in your mesh is you have to specify how big your elements are going to be. Okay. And depending on how big your elements are going to be, that's going to determine how big your mesh is. Okay. And so where you have to assign that is on this option right here for global max edge size. Okay. And that basically specifies how long an edge is going to be in your elements. Right. And so if you're not sure what to pick, SimVascular comes with an estimate option. And so you can go ahead and click estimate for the global max edge size. And SimVascular is recommending an edge size of approximately 0.2. Okay. And so, just as your first mesh, I would recommend going with the estimate here and then click run measure. Okay. And so if you're following along right now, go ahead and click estimate global max edge size and then click run measure. Okay. And then after you click run measure, it's a window is going to pop up and it say the meshing may take a while. Do you want to continue? And then you click yes, because you know more than SimVascular and you're not going to take any advice from them. And so you're just going to go ahead and click yes. And then it's going to take some time to create your mesh. And so, depending on how strong your computer is, this step might either be kind of fast or it might take, a few minutes. And so, it's going to look like the program froze because it's going to say not responding here. And so that's actually kind of good that mine said that. But if you check on the bottom left of your screen, it should say, creating mesh for them. And then when the mesh is done, it's going to give you some mesh statistics here. Okay. And you can see for this mesh, it produced a mesh with a number of elements of 257,000. And so there's basically 257,000, little tetrahedrons here. And you can see the number of nodes and edges and faces right there. Okay. And so for everyone who's following along, were you guys able to produce a mesh? You guys might have a different amount of elements. And so, if it's not exactly 257,000, don't worry about it. You didn't do anything wrong. It's just, the meshing, there's a little bit of randomness to it. And so it's not going to be exactly the same for everyone. Okay. All right, great. So it looks like you guys are is able to produce the mesh. And so from here, we can investigate the mesh. And so if you can kind of zoom in, actually, we have our model turned on right now. And so if you want to see just the mesh, you can turn off the demo model here, okay? And you can see here, here's the mesh that we produced, okay? And so you can see here that, we've taken our geometry here and we've broken it up into a bunch of little triangles on the surface, okay? And this mesh has 250,000 elements. And if you forget the number of elements that you chose, that you had, you can go ahead and click this mesh info button right here. And this mesh info will bring up the number of elements that you have. Okay. And so the number of elements is a very important statistic. And so, make sure that you're kind of always aware of that, because that's going to determine, how, first of all, how many processors that you're going to run your simulation with, but also ultimately the accuracy that you're going to run with as well. Okay. And so, make sure that you're always kind of aware of the number of elements. And if you forget, just click this mesh info button here on the top right. Okay. All right. And so if you reduce the size of the elements, you're going to produce a mesh that's more fine or more coarse, right? And so let me show you kind of a case where let's make the mesh more coarse. Instead of 0.2, let me manually change this to 0.3. Okay, and let me run the mesh again. And so you don't have to do this, and so this is kind of just for your just for your education. Okay. And you can see that when I change the mesh size, when I change it from 0.2 to 0.3, we end up with a mesh with a lot less elements. And so instead of 257,000, now we have a mesh with 76,000. So that's a pretty big reduction there. Okay. And so, if you want to make the mesh more coarse, you can go ahead and do that. Okay. And so this simulation will run a lot faster, but it's not going to be as accurate because you don't have as many elements, right? And so just, for demonstration, I'm going to go ahead and reduce the mesh size. And so if you don't have confidence in your computer, then I would not recommend this, because it literally might crash your computer. But I'm going to go ahead and try with the mesh element size of, let's try 0.12. Okay. Let me go ahead and run this mesher. It's going to take a little while, so let me go ahead and do this. Okay. All right, question in the chat. Great question. So how fine do I want your meshes for your project? Yeah, it's a great question. And so for your projects, so ultimately, the answer to that question is, generally you want to run what's called a mesh convergence test. And so what that means is, you want to run your simulation under a bunch of different mesh densities and see what gives you, the most accurate results. But we just don't really have the time to do this in this class. And so if you can produce a mesh that's within the range of 1 million to 2 million elements, that's going to be pretty good for this class. But of course, if your computer's not able to produce that mesh, anywhere that's above, anything that's above 250,000 should be good for this class. Yeah. Right. Okay, so if you're following along with your model and you have a estimated mesh size of 0.012, and so that seems really small to me. And so if you try to create a mesh with that, you might end up crashing your computer. And so I think probably what's happening right now is there might be something in your model that's making the edge size that small. And so I would oh, it created it. And so how many elements did you end up with? Okay, so if you have elements that are like maybe about like 1 million, 2 million, then that's fine. But if you have something that's like 5 million, 6 million, or 10 million, then that would be difficult to run. And so kind of right now, I know we're running with a supercomputer, but there's I only requested so much time for this class, and so we can't run anything too heavy, unfortunately. And so I want to keep it within like the range of 1 million to 2 million. Yeah, so just check the number of elements, and if it's within that range, then you're good to go. But if not, then it's we need a course in that mesh. Yeah. Okay, and so with the mesh size of 0.12, then I ended up with about 1.2 million elements. So this is pretty good for this project. Okay. And of course, depending on your geometry and the actual size of your CAD model, the number of elements that you pick and the size, and the size to number of elements correlation is going to be different. And so I would say this model right here of the aorta is pretty big. And so aorta models tend to be, pretty beefy, just because the aorta is the biggest blood vessel in your body. And so I know a lot of you guys are doing aortas for your project, and so you might end up with similar sizes as this. And of course it depends on the size of the human that you're measuring too. And so if you're doing like a small kid versus like maybe like a linebacker, then you're gonna end up with a different mesh size for your models. And so definitely play with the mesh size and see what number of elements that you end up with, and then go from there. But you want to be in the range of about 1 to 2 million elements. Yeah. Okay. And so, that's kind of just the basics of meshing. And so, there's a lot more that you can do with the mesh here. And so, if we have time kind of later in the class, I would love to kind of go through this. But, just for this project, the only thing you really need is just kind of a basic mesh. And so I just want to stick to this for this workshop. Yeah. 1.4 million. Okay. Yeah, that's fine. And so that sounds good for this project. Yeah. Great. And so if you guys, if for reference, if you guys want to compare this class, and I know some of you are in 410 as well, and so you guys will appreciate this a bit more. And so for my other finite element class, where we're using ANSYS, which is a commercial software, but we're using a free version. The limitation that you have in ANSYS is only 32,000 elements, and that's running on your personal computer, right? And so for this class, we're going to be running meshes up into the millions. And so we're going to be 1 to 2 million. So that kind of gives you an idea of, the amount of power that you're going to have access to with the supercomputer, for this class. And so it's, it's a unique opportunity because, a mesh with 1.2 million, you're not going to be able to run this on a personal computer, and ANSYS definitely would not allow you to run this on your personal computer as well. And so the fact that we're able to drive the element count this high and we're running on a supercomputer, it's a pretty unique opportunity for this class. All right, but for this tutorial, because I do want to run the simulation on my laptop just to show you, I'm going to go ahead and coarsen this mesh, and so I'm going to change it back to 0.3. And so this will put me in 76,000. And so if your mesh is less than 100,000 elements, you can probably run that simulation on your desktop. But if you're creeping up on like a million stuff, then you probably want to run that on the supercomputer. But for this workshop, I'm going to run this on my laptop, and so I'm going to coarsen this up to about 76,000. Okay. Okay, and so that's the basics of meshing. And so try to get your mesh within that range, about 1 to 2 million, and then you should be good to go. Okay. All right, and so now let's actually start to set up the simulation itself, okay? And so we're going to set up things like, the properties, the fluid properties, the boundary conditions, and all of the other solver parameters, okay? And so to create a simulation job, you're going to right-click Simulations from the Data Manager, and then you're going to click Create Simulation Job right here, okay? All right, and so, after you click Create Simulation Job, you have to give your simulation job a name, okay? And so I'm going to call this test job. Okay. And so from here, we're basically be running through all the different, aspects of this, of setting up the simulation. Okay. And so let me go ahead and turn off the mesh. And so let me go ahead and disable test mesh here. And let me click this check mark here for show model, just so that we can kind of see, what we're working with. Okay. Okay. And so the first thing that we're going to do is we're going to set up the fluid properties, okay? And so we're going to set up things like the density and the viscosity and some other stuff, okay? All right, and so luckily for us, the fluid that we're going to be working with is going to be the same for everyone. And so, we're all going to be simulating blood. And so, we're not going to be doing vampires or, anything like that. And so, everyone has the same blood. And so we're going to all work with the same density. We're all going to work with the same viscosity. And these are already configured to be, the correct values for blood, because that's what people use SimVascular for, okay? And I think the units, if you want the units for this, I think this density is given in terms of grams per centimeter cubed. And then this viscosity, I forget the exact units for viscosity, so I think it's in CGS units. Yeah. Do you get extra credit if you do it for vampire? If you can find out the density of vampire blood and the viscosity for vampire blood, and you have a scientific paper to back that up, then I will give you extra credit for that. But to my knowledge, no one has been able to measure the density of or viscosity of vampire blood. But if you can find that out and find a scientific paper to back that up, then I will give you 5 points extra credit for it. Yeah. All right. And so, luckily for this, we don't have to do anything. And so even for this stuff, and so, you're probably wondering, what is the IC file? And so IC it's not a frozen beverage that you get from AMPM, but IC here stands for initial condition. Okay. And so, one thing that you can do if you want is that you can specify, a file that will specify all the velocities and pressures throughout your entire domain. Okay. And so if you don't specify this at the beginning of your simulation, it'll basically assume that the pressures and velocities are basically close to zero. Okay. If you discover vampires, yes, then I'll give you 5 points extra credit. But you'll probably be earning a lot more fame in other places as well. And so if for some reason you want to start your simulation from someplace that's not 0, 0, then you can do that here. But for this class, starting from 0 is totally fine. Okay. I will say that if you do want to run a deformable wall simulation, and I know some of you guys might have some interest in doing that, then you do have to play with these parameters here. But if you are just running a rigid wall simulation, then you don't have to fuss with these, and you don't have to set anything here. So that's totally fine. But this initial condition, initial pressure, this is really only if you want to run a deformable wall simulation. But if you want to run just a basic rigid wall simulation, then this is perfectly fine. So starting from 0. Okay. Okay. And so now that the basic parameters are out of the way, the next thing that we're going to set are the inlet and outlet BCs. Okay. And so BCs stand for boundary conditions. Okay. And in particular, we want to set the conditions on our caps. Okay. And so these are for the inlets and outlets. And so if you go back to our slides here, the inlet and outlet boundary conditions, these specify the behaviors. This specifies the behavior of the solution at the locations where we expect flow to pass through, right? And so for a SimVascular model, basically we expect flow to go through this cap right here, and we expect it to go, all throughout the model, and we expect it to exit out of these outlets right here at the end, okay? And so the inlet and outlet BCs, this will allow us to specify boundary conditions at all the caps of our model, okay? Okay. And so at this point, you have to kind of go back to step 1 of your simulation process, right? And you have to kind of ask yourself, where is the flow coming into the model, and where is the flow going out? Okay, because these are really important, because the boundary conditions that we specify are going to be different at the inlets and outlets of our domain. Okay, and so for this particular model, and since we're doing the aorta, basically what we're going to assume is that the blood is going to come from above, because that's where the heart is. The heart is kind of in this area right here, and so the flow is going to enter from here. Okay, and so this cap right here is cap aorta. Okay, and so when you click this here, you can see that it's highlighted. Okay, and so flow is going to enter from here, and it's going to flow through your model, and it's going to exit out of the legs. And so this is the iliac arteries right here. Okay. And so if you're running an aortic model for your project, you'll probably have only one inlet that you need to worry about here. Okay, but if you're running a different model, a model without an aorta, probably you need to probably will need to touch base at some point, so I can tell you where the flow is coming from and where it's exiting. Okay, but if you're running an aorta model, which is most of the people in this class, you're going to be, specifying the flow at the aortic inlet, okay, which is right here. Okay, and so let's start with that first. And so let's learn how to specify inlet boundary conditions. Okay, and so with cap aorta highlighted here, first thing we have to do is we have to specify a boundary condition type. Okay, and so if you double click this, then a drop-down menu will appear, and you can see that, we can specify 4 types of boundary conditions, okay? For everyone in this class, you're only going to be worried about the first 2. And so the first boundary condition here is called a prescribed velocity boundary condition. And this is the type of boundary condition we're going to specify at our inlets. And this basically allows us to specify the amount of inflow that goes into our models, okay? And so basically, if you have an inlet boundary condition, you're going to specify a prescribed velocity type of boundary condition, okay? And then for the outlets, we're going to specify a resistance boundary condition, okay? And that resistance is basically going to be, you can kind of think about it like our LPM resistances. And so what that's going to do is it's going to specify a pressure type boundary condition where the amount of pressure is going to depend on the amount of flow. And so what you have is basically an Ohm's law relationship over there, okay? And so you can also specify an RCR type boundary condition. And so that's our Windkessel model. And you can also specify a coronary boundary condition if you have a coronary model. But for this class, I'm going to steer clear from these because, setting up the RCR and coronary boundary conditions are a little bit convoluted, a little bit complex. And so, for this class, I'm going to stick to just the resistances and just the prescribed velocity boundary conditions, okay? Okay. And so since, for this cap right here, this is a inlet, and then we're going to do a prescribed velocity, okay? And so that's the type of boundary condition we're going to specify. But we're not done here yet. And so, not only do we have to specify this as a prescribed velocity, we have to actually specify its parameters. And so after you've selected this as a prescribed velocity type of boundary condition type, what you're going to do is you're going to double click on the name of that cap. And then by doing that, you're going to bring up another window here. Okay. All right. And so let me pause here for questions. So are there any questions or as if people are you guys able to bring up this window here for the prescribed velocity boundary condition? Great. Great. Excellent. Okay. All right. And so here we're going to specify the parameters for our prescribed velocity. Okay. And so first thing we're going to specify is the shape of the velocity profile. Okay. And so what that means is, ultimately, we're going to be prescribing fluid velocity here on this surface. And we need to specify how those velocities are going to vary in space on the surface, okay? And you have a few options here. And so you have, first of all, a parabolic profile. And so that's kind of the standard profile that you have for pipe flow. And so that's going to assume the velocity is shaped like a parabola. And so a parabolic profile is a great option. And so, I would say go ahead and pick that, okay? You can also pick a plug option. And so what that basically assumes that the velocity is kind of uniform throughout the surface. And so because it kind of looks like a flat plug, I don't know what a flat plug looks like, but that's kind of what they describe it as. That's what that is. And so plug profiles are used when the flow hasn't had time to develop. And so it's actually a common boundary condition if you have the aortic arch, which is what a lot of you guys have in your project. And so if you have the aortic arch in your model, where you're basically simulating the blood right as it comes out of the heart, a plug profile is pretty common for that because the blood is being just ejected from the heart and it hasn't really had time to develop. And so a plug profile is good for that. Okay. And so the last option here is Walmersley. And so don't worry about Walmersley yet. And so we're gonna go over that kind of post spring break. And so that's another type of boundary condition that works well if you have kind of an unsteady velocity profile. But for your projects, I'm only requiring you guys to have a steady simulation done. And so, we're going to stick to parabolic for that. Okay. Because that kind of gives us a good option for that. Okay. Okay. And so the next two options here for point number and Fourier modes, don't worry about these too much. You can kind of leave these as the default value. So these default values are good right here. And so, you're going to hear me say that a lot about these simulation parameters because, to go in and kind of explain what every single simulation parameter does is unfortunately would take a few weeks because there's a lot of stuff here. But thankfully, a lot of the defaults here are pretty good already. And so you don't have to kind of mess with those. And so with these, basically what you can think of it is, SimVascular is going to do a Fourier approximation of your inflow file, and this kind of sets the parameters for that Fourier approximation. And so if you remember a little bit about Fourier from maybe your from your 308 classes, then you might have kind of understood that a little bit. But if you didn't, then don't worry about it. It's not that important for this class. And so if you have a point number of 201 and 10 Fourier modes, that's plenty. And so I haven't run into any situations where that hasn't been good enough. Okay. Okay. And so the next thing that we have to specify here is the flow rate file. And so this is probably the most important thing, okay? And so if you can see from here, there's a button with 3 dots. And so from here, it's going to ask you to upload a .flow file, okay? All right, and so actually, let me show you what that file looks like, before we actually go into that. Okay. All right, and so inside that demo project folder, and so in addition to being the SimVascular project, you'll see that there's another folder here called flow files, okay? And if you open that folder, you can see that there's only one file here. And so the name of the folder is obviously in lie. And so there's only one file here, okay? And so what the flow file here, you'll see that it's basically just a text file that has numbers, okay? And to basically kind of illustrate what this is, let me kind of graph this for you. And I'll show you what it looks like. And my fiance's at the door. Let me tell her that I'm lecturing right now. Okay. Okay. And so what I've done is I've taken this steady flow file right here. And so I have 2 columns here. And then I'm going to go ahead and paste that into this Excel sheet. And that did not work at all. And so I'm going to put in these numbers manually. Usually what you can do is you can just copy and paste these into an Excel sheet and you can graph it. But for some reason, that's not working here. Okay, and so the way that you can kind of interpret this flow file here is that there's basically 2 columns of data. And so the first column here is going to be time. And then the other column here is going to be flow, okay? And so the units for time are obviously going to be in seconds, okay? And then the flow here, the units for this is usually going to be in milliliters per second, right? And so you don't have to do this, and so you don't have to go into Excel and graph this. And so this is more just to showing you what's inside this file, okay? And so what I can do here is I can basically graph this. So that didn't work. It's been a while since I've done Excel. Scatter plot within line, no. Why is this so difficult? Yeah, so if
Professor,
you
can click on recommended charts and maybe that right there in the middle, recommended charts.
Oh, recommended charts, yes.
Yeah. Maybe
Okay, there we go. Yeah, and so basically you can see here, so on this x-axis here, we basically have time. So let me go ahead and add that. Yeah, so if you don't have this file, you can go ahead and create this. And so it's just a simple text file. And so basically all you have to do is just open up Notepad and just have kind of the same file. Okay. And so if you didn't have this file, what you can do is you can open up Notepad, okay? And you can do basically the same thing. And so you can just input 0.0 and then do a space -100 and then enter 1.0 and space -100. Okay. And you can just save this as a flow file. So there's nothing unique about this file. It's just a simple text file. And so if you don't have that, you can basically just kind of recreate this from scratch yourself. Okay. All right. And so what this flow file specifies is the amount of inflow or the amount of Q that we're going to be inputting into our model as a function of time. Okay. And so if you notice from this flow file, it's called steady, right? And so what we're inputting here is just a steady flow file. And so from 0 to 1, basically, we're going to be inputting a steady amount of flow of 100 milliliters per second. Okay, and so if you just want to run a steady simulation, all you have to do is just make a text file like this, and specify that that thing. Okay. The caveat here is that this assumes that your flow rate. Oops. is 100 milliliters per second, okay? Which basically assumes that your cardiac output for your patient is 100 milliliters per second, okay? And so this might not be true for your patient. And so, for your final projects, you have to really think about how much inflow that you want to specify. And so if you kind of remember, for your models, there's kind of the PDF document that comes along with it. And so if you're lucky in that PDF document, they'll tell you how much flow that you want to specify in. But if that PDF doesn't tell you, you're going to have to do a little bit of extra research yourself into what's the typical amount of flow that goes into this part of the body. Okay. But for this particular simulation, we're going to run with the flow rate of 100 milliliters per second. Okay. Yes. Yes. Yeah. So that's a good question. And so these two 100s right here are negative. And so, and the reason it's negative is because we're kind of using the convention from fluid mechanics. And so basically, if you have a negative amount of flow, that tells you that the flow is going into your model. And so, probably for you guys, it might have been a while since you've taken fluid mechanics, but if you kind of remember from control volume analysis, if you have a negative velocity or a negative amount of flow, that means flow is going into your control volume. If you have a positive amount of flow, that's flow coming out. And so we specify negative flows here to basically make sure that the flow is going into our model. Okay. Yeah. So you want to make sure that when you create your flow files that you do use negatives here in order to input that. Okay. Okay. And so if you have the steady flow file, you can go ahead and use it. If not, you can go ahead and create it on your own. But what you need to do is you need to upload that into SimVascular using this menu here. Okay. And so coming back into SimVascular, making sure that you have this prescribed velocities window open, you're going to click this button here with the 3 dots, and then you're going to go and then upload that steady text file that you had before. Okay. Okay. And so, it might take you a little while to find it, but, this is where mine is. If you want to put yours on the desktop, that's fine too. Okay. And so after you load that in, you can see that, it should have the name of your file here, and it should automatically produce the period for your simulation as well. Okay. Okay. And so this part's really important. And so, when you're working on your final projects, you want to make sure that you specify the right amount of inflow for your model. Okay. And if you want for your project, I'm only requiring that you do a steady simulation for your project. But if you finish the steady simulation early and you want to run an unsteady flow, like you have something with a pulsatile flow waveform, then you would basically modify this right here, and and we can talk about that once we get to that point. But for now, I just kind of want to stick to kind of the basics of the simulation. So we're going to specify just a steady flow file here. Okay. All right. Any questions on this so far? Okay. All right. And so that's the inlet boundary condition. And so now let's specify, make sure you click OK. And so when you click OK, you should see assigned right here. Okay. And now let's specify the outlet boundary conditions. Okay. And so for the outlet boundary conditions, we're going to assume that both of them are resistance outlets. Okay. And so go ahead and double click both of these and change them into resistance outlet boundary conditions. Okay. And so what that's going to do is going to put an LPM resistor at these outlets. And what that's going to do is it's going to specify a pressure boundary condition on these outlet surfaces for the simulation. Okay. All right. And so what we have to do here is we have to actually specify, the amount of resistance, right? And so it's not only enough to specify, that we want a resistance outlet, we have to give this a value, right? Okay. And so the question now is, what do we specify for these resistance outlets? And so the nice thing about SimVascular is that it has kind of a nice way to specify all of your resistance outlets based purely on just a total resistance. Okay. And so what I want you guys to do is after you specify both these caps to have resistance boundary conditions outlets, then I want you to highlight both of them by holding control on your mouse and clicking, and then right click on there. And then after you right click with both of them together, you want to click on the button for split resistance. Okay. Right. And then after you click on split resistance, then you'll have this new window pop up right here, okay? And you'll see that you need to input 2 parameters here. And so the first thing that you need to input here is total resistance. And so we'll go over that in a second. And then the second quantity that you want to have here is your Murray's law coefficient, right? And so if you remember, when we went over Murray's law, before, this is kind of the coefficient or the exponent that goes into Murray's law, okay? And so the default value for Murray's law coefficients is 2, but anything between 2 and 3 is fine, okay? And so of course, the exact number for the Murray's law coefficient depends on the vessel that you're doing. And so in this case, since we're doing aortic vessels, which are fairly large, I think these ones we select a fairly low Murray's law coefficient. And so let me pick a Murray's law coefficient about 2.2. But you can choose, make sure you choose one that's kind of appropriate for the type of model that you're doing. Okay. All right. And so the next thing that we have to specify here is the total resistance. Okay. And so for the total resistance, what you want to do is you want to use your Ohm's law, your Ohm's law expression here. Okay. And so let me open up a notepad here. Okay. And so for the total resistance, remember from Ohm's law, the way that we specify this, and let me make the font size bigger. Control plus, right? Ultra zoom, okay. And so remember for Ohm's law in, for our LPMs, what we had was P is equal to Q times R, right? And so pressure was equal to, flow times resistance, right? So that was our kind of our Ohm's law expression for, for our LPM models. Okay. What we're going to do is instead of solving for pressure here, we're going to invert this equation to solve for R. Okay. And so instead of P is equal to Q times R, what we're going to have is R is equal to P divided by Q. Okay. Where this R right here, this R is our total resistance. Okay. And so this is kind of, very similar to, what we were doing when we were tuning our LPMs, right? And so a lot of you guys wrote about this in your midterm exams that, if you want to tune the resistances, you have to take the pressure that you have in your model and you have to divide it by the flows. Okay. And so we're going to do the exact same thing here to compute the total resistance. Okay. The only thing you have to make sure to do is that you have to make sure that everything here is in the appropriate units, which we kind of glossed over a little bit in our LPM units, in our LPM chapter. And so when we were talking about LPMs, we didn't really talk about the units for these kinds of for these parameters here. But when you're specifying these boundary conditions, the units are extremely important. Okay. And so let me tell you the units that you need to use to input into this formula. Okay. And so let's talk about P first. Okay. And so the units for pressure that you need to input into this formula here are going to be in dyne per centimeter square. Okay. And so, you've probably never seen that unit of pressure before. And so, what this unit of pressure is, this is the units for pressure in the CGS unit system. Okay. And so CGS stands for basically centimeters, grams, and seconds. And so it's a unit system that's used for medical stuff. Okay. And so, what you can do is you can basically take a pressure and you can use Google Converter to convert for you, right? And so let's say that you have an average pressure in your model of 90 millimeters of mercury, and so that's pretty typical for a person. Okay, and if you want to convert this to dyne per centimeter square, you can do 90 millimeter mercury to dyne per centimeter square. Okay, and you can see right here that the value that you get is this. Okay, and so this is the pressure that you want to input into your resistance equation. Okay. But actually, there's the conversion actually from millimeter mercury to dyne per centimeter square is actually really easy. And so to convert this, basically what you do is you take your pressure in millimeters of mercury, okay, and then you're going to multiply it by 1333, 1333, okay. And so what this will do is this will convert your pressure from millimeters of mercury to dyne per centimeter square. Okay. And so a lot of times, you're going to see pressures in millimeters of mercury because this is the unit that they typically use in the clinics a lot, right? Like you go to CVS and you stick your arm in the machine, it tells you that your pressure is 120 over 80. And so that 120 and 80, those are pressure units given to you in millimeters of mercury, okay? And so, if we open up a calculator, okay, thankfully this is huge already. And so let's say that we have a pressure of 90 millimeters of mercury, okay? And then we want to convert this to dyne per centimeter square. And so we're going to multiply by 13333, okay? And we end up with 119,970, which is, about the same here. And so the conversion factor isn't exactly 1333, but it's kind of easy for me to remember because it's very close to LEET, which is, what I was, in my younger years, but I'm no longer LEET anymore. And so I just use 1333, okay? Okay. And so your pressure needs to be in dyne per centimeter square. And then your flow needs to be in milliliters per second, okay? Okay, and so let's take that information and let's compute, the total resistance for this model here. Okay? And so for this model, let's say that we have an average pressure of 90 millimeters of mercury, okay? And we have a flow rate of 100 milliliters per second, okay? And so our resistance here is going to be 90 millimeters of mercury times 1333 divided by 100, okay? And so let's go ahead and punch that into the calculator. And so that's going to be 90 times 1333 divided by 100. And we get a total resistance of about 1200. So it's basically 1200 right on the nose, okay? And so let's go ahead and input that 1200 into our total resistance here, okay? And then we're going to click OK. And then after you click OK, what you'll see is that SimVascular will automatically take that total resistance and then split it among the different outlets in your model, okay? And so, with the outlet resistances of, 2,151 on this cap and then 2,700 on this cap, that gives you a total resistance of about 1,200, resistance units, okay? And so that's kind of a nice thing. And so, in SimVascular, all you have to really do is compute the total resistance for your entire model. And then SimVascular will basically split that resistance, among the different outlets based on some Murray's Law coefficient. Okay. All right. So any questions on that? Okay. All right, and so we're almost out of time. And so I'll save the solver parameters for later. And so we'll do that another day. And so the last thing that I'll talk about today is setting the wall properties, okay? And so remember the wall boundary conditions, those are the boundary conditions on the sections of the model where the flow is not going to pass through, right? And so we don't want the flow to pass through here, okay? And so for SimVascular, it's very easy. And so you only have basically two different options. And so you can either have a rigid simulation where it assumes all the walls are perfectly rigid, okay? Or you can have a deformable wall simulation. And you can either have a deformable wall simulation where the properties are constant, or a deformable wall simulation where the properties are variable. And so for this class, we're just going to assume rigid wall boundary conditions. And so you can just specify rigid here, okay? And so that's all that's going to be required for the project. But if you are interested in running a deformable wall simulation, then we can touch base later, and we can kind of work that out in office hours and things. But to start with, for your first simulation, I would highly recommend that you run rigid, because deformable wall simulations take quite a bit of setup, and so it's not kind of the most straightforward thing. And so that's something that I would want to work together closely with you in order to make sure that that's going okay. Okay. All right. And so I don't really want to get into the solver parameters because there's kind of a lot to talk about here. And so we'll do that on Thursday. And so any final questions that I can answer before we close up for today? Okay. All right. And so that's all we got time for today. And so thank you guys for tuning in. And so on Thursday, we'll continue this and we'll finish up the workshop on SimVascular simulations. And so I'll show you how to run the simulation, how to run it on the cluster, and then how to view the results as well. Okay. right, so thank you guys for tuning in. I know this is a kind of a not the easiest week to tune in because it's right before spring break, but I appreciate you guys coming out. And so have a great rest of your evening, and I'll see you guys on Thursday. Thanks, guys.
Professor,
Yep.
so that patient information, was that part of or the PDF, was that part of the link that you provided to us through Dropbox, or is it on the website?
It's on the website. And so
Okay.
actually, let me see. I might have the reports that I might be able to give you guys. So I might be able to put it in the Dropbox for you. I just wasn't really looking for it.
Oh, okay.
Let me see. What's your let me check for yours first. So what's your model number?
It was, let me see.
Or I can pull it up too. Let me see.
It's OSM SC006.
006. Okay.
Yeah.
Let me see. Oops. 006. Let's see. Extras. What's this? Okay, yeah, I do have the PDF. So let me go. I'll go through and I'll add the PDFs to the Dropbox links, and so you can kind of access them. But you can read these from the website. But let me put these in the Dropbox just so that you'll have them. You'll have them. You'll have them all in one place. Yeah.
Okay, for sure. Thank you so much, Professor.
Yep. Mm-hmm. All right. Did you guys have any more questions? Okay. And so if you guys don't have any more questions, I'm going to go ahead and close the call. And so thank you guys for tuning in, and I'll see you guys on Thursday.